Welcome everybody to in 19.3. It's a very exciting section. It's going to blow your mind. Actually, it's about the same as the rest of the chapter, but I know people are a little fatigued at this point, so I just wanted to give you a little, boost in enthusiasm. Okay, so 19.3 is the second to last section of chapter 19. It's focusing on the equilibria of slightly soluble ionic compounds. So remember from your previous chemistry class that you had solubility charts, and often they were kind of bifurcated into soluble species and insoluble species. Remember, if something is soluble, it's gonna have that little AQ next to it as its state of matter, and if it's insoluble, then you'll see an S for solid. It forms a precipitate. So there's actually a category that's kind of in between, and that's those that are partially soluble. So at a certain point, they will remain solid in the solution. And really everything has a limit to how much can actually dissolve in the solution. Sodium chloride is particularly soluble in water. However, there's a limit for sodium chloride too. There's only so much salt you can put into water until it continues to be a solid. But we're going to focus on a category that is really in between. They have a really kind of low solubility, but some does actually dissociate into solution to create ions. So the way to analyze that is we're going to be looking at what's called the ion product expression, or QSP, and the Ksp solubility product constant. Now, in these scenarios, water is going to be the solvent. And the Q and K that we're looking at really are not different from our chapter 17, Q and K. Q means current conditions, what is currently in the solution. And K is, at equilibrium. Really, in this case, it's at saturation. That is what is in the solution. So we're using a generic expression. We have a solid, an ionic compound, that when it's placed into water, it dissociates into its cation and anion, and we can set up an expression based on the concentration of those ions. And really, this is products over reactants, but my reactant is a solid. Therefore, I'm going to put 1 on the denominator, and that's what I have written down here at the bottom. So again, the ion product expression is just equal to the concentration of the ions, and make sure to apply the coefficients as exponents where necessary. The Ksp solubility product constant is the same basic setup as the QSP, except these are at saturation. That just means the maximum amount of ions that can be in the solution at that point. And this is temperature dependent, so this depends on temperature. So as temperature goes up, generally the amount of ions that can be dissolved in the solution increases, so the solubility increases for those ions. So dependent on temperature. As a reminder, these little brackets right here are moles per liter, so molar solubility. Molarity is going into those brackets. And the last thing you might be wondering is, what does the SP stand for? S stands for solubility, or it's representing solubility product of a particular compound. So S for solubility and P for product. And it's letting you know that it's a K or Q expression specific for the solubility of an ionic compound. On our upcoming exam for chapter 19, you will not be tested on the special case of metal sulfides. However, we will be using this for our qualitative analysis lab. So you will need to be familiar with it, but again, not for the chapter 19 exam. Okay, so let's jump right in with an example question. So example question 1 says that lead 2 sulfate solubility is 4.25 times 10 to the negative 3 grams per 100 milliliters at a particular temperature. what is the Ksp of lead 2 sulfate? And then the molar mass is given. So let's identify and kind of flesh out some of these terms, talk about what they mean before we try to set up this problem. Okay, right here when you see solubility. Solubility of this compound, this means the maximum amount of solute that can dissolve. So this is maximum solute that will dissociate or dissolve. It'd be helpful if I could spell that. Dissociate. Okay, and then it's given in units of grams per 100 milliliters. So that just means you have a little beaker with about 100 milliliters. You could actually dissolve 0.00425 grams in to make a 100 milliliter solution. All of it would dissociate. All of that mass would dissociate. Okay, but if I add any more, it's going to stay as a solid. And the question is, what is the Ksp? All right, first thing that you want to do is write out the reaction. So what is actually happening in this reaction when it's dissolving? Well, it's pretty simple. It's just the solid dissociating into its ions. Great. Second thing we want to do, since we want to solve for the Ksp, is write the Ksp expression. So the ion product constant expression is going to be equal to products over reactants. So that would just end up being concentration of lead, and that's at saturation, times the concentration of sulfate, also at saturation. All right, the third step would be to set up an ice table. So that will be underneath the reaction. The point again is to solve for the Ksp. So I need the lead and sulfate concentrations at saturation, also known as equilibrium. So technically they're at saturation and equilibrium. So we're really looking for the E values at the very end. Okay, so I think the easiest way to set up the ice table is actually to input X values instead of numerical values, and then we can plug in the numbers at the end. So right here, this initial, what does this mean? These are going to look a little bit different from our previous ice tables, because when we've been dealing with solids in the past, we haven't been including them. But again, the ice table is a tool. It's not a physical reality. So we just use it for whatever is helpful for us. So in this case, what we're going to be putting in I for any of the solids we're using in 19.3, that's going to represent solubility, the maximum solubility. Generally speaking, it's going to represent molar solubility, which is moles per liter. So what I want to put right here is my molar solubility, and I'm just going to, for now, I'm just going to input X. Okay, I'm going to put X. So again, this little I is going to be molar solubility. That's what you'll put in from now on. And before the dissociation occurs, there's 0 moles per liter of lead 2 and sulfate. Okay, what's the change going to be? The change is going to be based off your X, because we're what molar solubility means, or what solubility means, again, is that the maximum solute that will dissociate or dissolve. So this is the maximum amount that I can put in. This X is the maximum amount I can put in and expect all of it to dissociate into the ion. So that means all of this is going to dissociate. And then on the right-hand side, I'm going to have plus X and plus X. So at the very end, I'll have 0, X, and X. So we're going to take these values, this X and X value, and we'll plug it in for the concentration or molar concentration of the lead 2 and the sulfate in the Ksp. So what we would have then is Ksp is equal to X times X, which is X squared. All right, but what is X? Remember, X represents the solubility. So what is given in the problem is solubility in grams per 100 milliliters. So this is actually pretty simple. What I need to do is just convert over into moles per liter. So X is equal to 4.25 times 10 to the negative 3 grams per 100 milliliters, and I need to convert that into moles per liter. So simple conversion into liters. There's 1,000 milliliters for 1 liter. Okay, so that would get rid of my milliliters. And then the next step would be to convert grams into moles. And I gave you the molar mass right here. So there's going to be 303.3 grams per 1 mole. And again, that would cross out our grams, so we would be left with moles per liter. So go ahead and do that calculation and press pause now, and then play when you're ready to check your answer. All right, this is your X value, 1.401 times 10 to the negative 4. We can plug that directly in here to find our Ksp. So go ahead and take that value and square it. I'm getting 1.96, let's see. Yeah, actually I think I underlined this wrong. This should be 3 sig figs, right? So it should be right there. We have 3 sig figs here, 3 here. Yeah, so our final should be 3 sig figs. So I think that gives us 1.96, yeah. 1.96 times 10 to the negative 8. All right, great. Let's move on to our next problem. Okay, our next problem states that we have lead-2 fluoride and its solubility is 0.64 grams per liter at a particular temperature. And the question is, what is the Ksp? So this is really the same question as A, except you have a different compound, so then you also have a different solubility. So I would suggest pausing the video now, and then when you are done solving the problem based on how we solved the previous problem, you go ahead and play. All right, so go ahead and pause the video now and attempt it on your own. Here is our solution. So let's walk through this together. First, we write out our dissociation reaction. Make sure you put the 2 in front of fluoride. Then writing out our Ksp, that 2 is applied to the exponent for fluoride concentration. Setting up our ice table, we start with X underneath lead-2 fluoride. Then make sure that you do apply that 2 in your change for 2x. Then at equilibrium, you should have x and 2x. This is where the majority of the issues happen, is that people forget to apply that 2. After I do that, I'm going to take my x values and plug them into my Ksp. Now, this is where another error happens, common error occurs, is that when you apply this squared, it needs to be applied to both this 2 and the x. So you should end up with 4x squared for this expression. Times x gives you a total of 4x cubed. Okay, here is the conversion from grams per liter to moles per liter. And this should say moles per liter of lead-2 fluoride. All right, then I'm going to take that value, the 0.00261, and plug it in for x right here. Make sure you cube it first and then you multiply by 4. So if you're doing it all at once in your calculator, you will need to have parentheses. Just make sure you have parentheses around that. And then you should end up with 2 sig figs at the very end, 7.1 times 10 to the negative 8. It is a unitless number. All right, so pause right here if you need to look over that for a little bit longer. If not, we are on to our next page. Now we're going to calculate molar solubility from the Ksp. The list of steps really are very similar, except obviously you don't have your x value, you don't have your solubility, so you have to solve for that at the very end. So let's start by setting up our dissolution reaction for calcium hydroxide. It dissolves into calcium ion. and 2 hydroxide. Make sure to apply that 2 there. And the Ksp is going to be equal to the concentration of calcium times the concentration of hydroxide, and both are saturated. Great, then we set up our ice table. This is our third step. So what we're representing for solubility is just x, 0 and 0, minus x, plus x, and plus 2x. So remember that 2 right here. And then at equilibrium, we have 0, x, and 2x. So it should look very similar to what we had in the previous problem. All right, now I'm going to take those values for calcium and for hydroxide and plug it into my Ksp. So we should end up with Ksp is equal to x times 2x squared. That simplifies a little further to x times 4x squared. And now the Ksp is equal to 4x cubed. All right, then we set that equal to the Ksp that is given to us up here, 6.5 times 10 to the negative 6. 6.5 times 10 to the negative 6. This is the order that I would solve for x. I would first divide by 4, and then I would raise each side to the 1/3. Make sure to keep those parentheses around the right side. So you'd end up with x is equal to, all right, your final answer should be 1.2 times 10 to the negative 2, and this would be moles per liter. 2 sig figs because 2 digits in the Ksp. All right, what about B? So B asks, what is the molar solubility in 0.1 molar calcium nitrate? Well, this is the molar solubility of the same compound used in part A, and that's calcium hydroxide. So let's use the information that's already given to us in part A. We have the dissolution reaction, Ksp, and the ice table. So the dissolution reaction says that calcium hydroxide splits up into calcium and hydroxide ions. Okay, so how does calcium nitrate impact that? How is that going to impact our final value? Well, nitrate doesn't show up in this reaction, so nitrate's really not going to have any impact on the equilibrium. However, calcium does show up. It's right here. So instead of having an initial value of 0, it looks like we're going to have an initial value of 0.1, which will change our final x value. So what I want you to do is set up 1, 2, and 3, the dissolution reaction, the Ksp, and the ice table. We'll solve for the x value together, but set those 3 elements up and then check back when you're done. All right, this is what you should have so far in terms of the dissolution reaction, Ksp, and the ice table. So these two look the same. The one that looks different is the ice table. You should start off with 0.1 molarity for the calcium since it is going into a solution that's 0.1 molar. So remember, we're looking at the calcium hydroxide as not dissolved yet. So it's a solid basically, and it's going to dissolve during this change. But at the beginning, we're looking at, okay, what is actually in the solution? Well, there's no hydroxide yet, but there's already a 0.1 molar solution of the calcium. All right, so the change is always going to be dependent upon the solid in this case. So we have negative x, and plus 2x. So at the very end, you should have 0.10 plus x and 2x. So let's go ahead and plug that into our Ksp. Ksp is going to be equal to 0.10 plus x and then 2x squared. And that is going to be equal to 6.5 times 10 to the negative 6, same as above. So because this math would get a little bit more onerous if we kept this x inside this expression right here, we'd end up with a more complicated polynomial. And chemists like to avoid that. They like to simplify as much as possible because we want values that are reasonable. And most of the time when you're dealing with slightly soluble ionic compounds, there's very little dissolution that's happening, very little ionization. So this x compared to the 0.1 is very, 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 very small. So we are going to assume that this is just equivalent to 0.10 times 2x squared. Okay, that simplifies it a lot. And anytime you have an initial value of one of the ions, it is going to be, if it's detectable, it's going to be so much greater than your x value that you can assume x is negligible. So at the very end, what you would get here is 0.10 times 4x squared, which would give you 0.4x squared. That looks like a weird 3. Okay, 4x squared. And this is all equal to 6.5 times 10 to the negative 6. Let's plug that in. So x should be equal to 4.0 times 10 to the negative 3. And because you already had some calcium in the solution, your solubility, or the amount of solid that you should be able to dissolve in the solution, should be lower than above. And it is. Times 10 to the negative 3 times 10 to the negative 2. And I did forget to put moles per liter. Okay, so that's the end for B. Pause it here if you want to take another look at this. If not, let's move on to effects on solubility. Okay, there are 3 major considerations when looking at the effects on solubility for a partially soluble ionic compound. So we're basically asking what's going to happen if we have, a solid and it is dissolving into, let's just say, cation and anion. So when solubility increases, that means the equilibrium is being pushed to the right. When solubility decreases, that means I am creating more solid. I'm pushing that equilibrium to the left. No change, then there's no push right or left for the equilibrium. Okay, so first is the addition of strong acid. That's one consideration. And we'll look at the specifics of each of these when we start to see some example problems on the next page. The second is the addition of an ion. The third is the addition of a common ion. And then anything else that you do to the solution that contains that partially soluble ionic compound has no effect on its solubility. So what I would suggest, since we're going to the next page, is to have these considerations in front of you so that you're able to reference them as we answer the questions. All right, so let's look at example question 1. How will the addition of strong acid affect the following compound solubility in water? All right, so that was consideration number 1. Consideration number 1, if you have that in front of you, says that the solubility is going to increase if the compound that you're analyzing contains either a strong base or if it contains the anion of a weak acid. Anion of a weak acid. All right, so let's use that for lead bromide. So what I would suggest you do in these problems is first write out the dissolution so you know what components are present during the dissolution. Okay, so the question is, how will the addition of strong acid affect the following compound's solubility in water? Okay, so first, does the dissolution contain a strong base? The answer is no, there is no strong base in there. Okay, so that doesn't apply. The second thing to look for is the anion of a weak acid. So you identify where the anion is, then this is my anion. Is this the anion of a weak acid? Well, what acid is it the anion of? It is the anion of hydrobromic acid. Is hydrobromic acid strong or weak? It's a strong acid. So bromide is not the conjugate anion of a weak acid. Therefore, there is no effect on solubility. So that would be the answer for A. I would suggest that you try B, C, and D, and then come back to see the answer. So pause it now, and then play the video when you are ready. Okay, here's our answers for how the solubility will be affected by the addition of strong acid, and let's look at why. Copper hydroxide. When you add a strong acid, hydroxide is in this dissolution. So you would have written out copper hydroxide like this. Copper 2. Hydroxide represents a strong base. If you have a strong base in this salt or in this ionic compound, the addition of a strong acid will increase solubility. That's what the arrow up is for. Okay, what about iron 2 sulfide? Okay, you're going to look at the anion. So iron 2 sulfide, when it dissociates, it goes into iron 2 and sulfide 2 minus. Oops, let's see, 2 minus right here. What is the conjugate acid? It's HS minus. That is an acid because it does have hydrogen in front of it, and you ask, is it strong or weak? It is weak. It's not on the strong acid list. So solubility increases. Same thing with carbonate. Carbonate is CO3 2 minus. The conjugate acid is HCO3 minus, bicarbonate. It is an acid, but it is weak. Okay, so the addition of a strong acid will increase solubility. So that's how you approach those types of problems. All right, let's go into predicting formation of a precipitate. Does a precipitate form when 0.1 liters of a 0.3 molar solution of calcium nitrate is mixed with 0.2 liters of a 0.060 molar solution of sodium fluoride? And here are the steps for the solution. So really before you look at this, I would suggest you write out, and I don't like red anymore, I'm changing this. You write out the balanced reaction. So you have calcium nitrate reacting with sodium fluoride, and you see what can form. This is going to undergo a double displacement, so the cations are going to switch places, and you're going to end up with sodium nitrate and calcium fluoride. So to balance this, you're going to have a 2 here and a 2 here. Okay, if you look on your solubility chart, which if you don't have one in front of you, you could pull one up online, you could look in your book, but if you're posed with this type of question on the exam, you will just have a solubility chart given to you, or I would tell you explicitly that calcium fluoride is the only compound that could actually create a solid. All compounds with sodium and nitrate, either one, if you just had sodium, just had nitrate, they're always going to be soluble. So they are not going to form solids. So calcium fluoride is the one that I am focusing on in this problem. So will a solid form? Well, it depends on whether or not you have enough of the ions in solution. Remember that once I get to saturation, after that point, everything else I put into the aqueous solution will be a solid. So until I'm at saturation, though, there will not be a solid. So step 1, since calcium fluoride is the only plausible, slightly soluble compound, write the dissolution reaction. All right, so the dissolution reaction would be calcium fluoride dissolving into calcium and fluoride ions. Excellent. Then I want to write, as step 2 says, the Ksp expression. So Ksp is equal to calcium times fluoride. Let me erase this so it does not get confusing. Squared. These are not going to be at saturation when you're actually just analyzing the Ksp. All right, and next, step 3 is solve for molarity of calcium ion and fluoride ion. So let me give you an example of what that looks like. So for calcium ion, I'm looking at the concentrations that are given here, and I have to take into consideration the final volume. So I would suggest to use M1V1 equals M2V2. M1 then would be this 0.30 moles per liter solution. V1 would be 0.100 liters. I don't know what M2 is. That is what I'm solving for. So right here, my M2 is unknown. So M2. Your V2 is going to be your total volume. So the total volume is going to be that 0.2 liters plus the 0.1 liters because those are mixed together. So V2 would be 0.300 liters. So do that same setup for fluoride as well. Pause the video, come back and check your answer. All right, you should have a 0.1 molar solution for calcium and then a 0.040 molar solution for fluoride. Okay, if you need any more time on that, go ahead and pause the video. If not, we are going to be looking at number 4. We want to plug the molarity values into the ion product expression, which is your Ksp. So this is step 4. Ksp is equal to, I'm looking up here, my calcium concentration 0.10, okay, times my fluoride concentration squared. So 0.040 squared. Okay, 0.00016. Now the question is, how does Qsp compare to Ksp? All right, the Ksp is given in number 1, right here. It looks like the Qsp is greater than the Ksp. So there are fewer zeros in front. This has 10 zeros in front. If you apply the scientific notation, this has 3 zeros in front. So the Qsp is greater. If the Qsp is greater, that means that solid will form. So solid will form. That means you're past saturation. You're past saturation. You have more ions than can be dissolved into the solution. So solid will be forming. All right, let's dig into this last problem for 19.3. It is about selective precipitation of different metals in a solution. This will be used by you in the qualitative analysis labs that will be coming up, unless you're just watching this for fun and doing it as a pastime, then those labs will not be coming up. Those are just used in my class. All right, so in the process of selective precipitation, a solution of one precipitating ion is added to a solution of 2 ionic compounds until the Qsp of the more soluble compound is almost equal to its Ksp. Now that sounds like a lot of gibberish, so let's look at how that pans out in an example problem. So a solution consists of 0.2 molar magnesium chloride, and this is supposed to say 0.2 molar copper chloride. So copper 2 chloride, CuCl2. Okay, calculate the hydroxide concentration that would separate the metal ions. So I think it's really helpful to kind of see a picture of what's going on. So let's pretend you have 2 test tubes and, oh, sorry, it's just 1 test tube, excuse me. 1 test tube, let's make it a little bit bigger. Okay, 1 test tube, and it has a 0.2 molar solution of magnesium chloride, and it has a 0.1 molar solution of copper 2 chloride. 0.10 of copper 2 chloride. Okay, so you can imagine some magnesium, and some copper. Now, the chloride isn't particularly important in this scenario because we're looking to precipitate the metals. Okay, so the magnesium and the copper right here. So the chloride's just there as a counter ion, right? So we want to know how much hydroxide I would need to add into this solution in order to precipitate one of them and not the other. So let's think of that really quickly. Which one is actually going to precipitate? So as I start adding hydroxide, which one's going to start precipitating first? To know that, you're going to look at the Ksp values. So the Ksp of magnesium hydroxide is 6.3 times 10 to the negative 10, and then the Ksp of copper hydroxide is 2.2 times 10 to the negative 20. This really, really small negative compared to this negative exponent means that copper hydroxide is going to start precipitating first. So this will precipitate first because it's less soluble. Okay, so that's really important to know when you look at a problem like this. Okay, what's the solution? So first we're going to write the dissolution reactions for both partially soluble compounds. Again, the partially soluble compounds are the ones that are going to form. So that's the magnesium hydroxide and the copper hydroxide. It's not these solutions. These ones are not the partially soluble ones. The partially soluble ones are the ones with the Ksp values given. Okay, so let's do that for number 1. So magnesium hydroxide. I'm not going to write the states of matter right here just for convenience sake. So it would look like that. And then copper hydroxide, copper 2 hydroxide would look like that. All right, then it says, we're actually in a calculation, calculate hydroxide for the more soluble compound, using the Ksp and molarity of the cation. So which one's more soluble? So we said that copper hydroxide is going to precipitate first, which means that magnesium hydroxide is more soluble. So let's write the Ksp for magnesium hydroxide. That's just going to be magnesium concentration times hydroxide concentration. I want to solve for hydroxide concentration. So that means Ksp over magnesium is going to equal hydroxide squared. I can square root both sides to get that hydroxide concentration is equal to the square root of Ksp over magnesium. Excellent. So what I need to plug in is the Ksp for magnesium hydroxide, and I need to plug in the magnesium concentration. So this one doesn't end up being diluted. The magnesium doesn't because it's already mixed with the copper. So I'm going to put 6.3 times 10 to the negative 10 divided by 0.20, square root it. This should give you 5.6 times 10 to the negative 5 molar. So that's the molarity of hydroxide that is needed to precipitate one of the ions and not the other. Let me explain this before we get into number 3, because this often throws people off. So people will say, well, copper hydroxide is the one to precipitate first, so why are we using the Ksp of magnesium hydroxide? The reason you are is because you want to add the maximum amount of hydroxide you can before precipitating only one of the metals. So I'm going to add as much as possible to precipitate, in this case, the copper, without precipitating the magnesium. So if I add enough hydroxide until right before the Ksp of magnesium hydroxide, that means I will create solid copper hydroxide, but I will not create any solid magnesium hydroxide. Remember, I need to go beyond the Ksp in order to start forming solid for magnesium hydroxide. But if I just go up to the Ksp, that means I will not precipitate any of the magnesium, but I will have precipitated all of the copper. All right, so step 3 says to check and see the cation molarity for the less soluble compound. This just gives us the amount left in solution. So this is just a check. It's actually not part of the problem. It's not the answer of to how much hydroxide I can add to the solution. It's really just to check to see how effective my separation of the two ions was. So let's do 3 right here. So it says I'm going to check the cation molarity for the less soluble compound. So that's copper hydroxide. So first I'm going to write the Ksp, because this will aid me in calculating the copper concentration. All right, the Ksp is given to me up at the top of 2.2 times 10 to the negative 20. All right, 2.2 times 10 to the negative 20 is equal to, okay, copper, I'm not plugging that in because I really want to know how much is left. Not how much I had before the precipitation. I want to know how much is left, assuming that I've used the total 5.6 times 10 to the negative 5 concentration for hydroxide. Okay, so I'm going to square the concentration of hydroxide, and then I'm going to divide it into the Ksp. I'm putting that into my calculator right now. And I end up getting a copper concentration remaining in solution of 7.0 times 10 to the negative 12. That's how much is left in the solution after I precipitate. That's a very, 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 very small amount of copper left in the solution, which means I've pretty effectively separated it out. Most of it is going to be solid at the very bottom of the test tube. Okay, so that's how separation between two metals works.